As always, we appreciate that you took time out of your busy schedule to join us. We know that you have many options on what you spend your time with, and so we are grateful that you joined us. We think we have a really exciting webinar today. The timing could not have been more perfect. We understand the Mars helicopter attempted its fourth flight today. I've not heard back on the results of it yet, so don't know how things went, but this is going to be a lot of fun. HAI Works webinar, Spinning Up, Designing the Blades for the Mars Helicopter. We have representatives from two great companies here that created the material for the rotor blades and then designed and built the rotor blades. So let's go ahead and get started. I'll go through our panelists for today. First of all, as always, our speaker, President and CEO, Jim Viola from here at HAI. We have Ben Pipenberg, who is the engineering lead for Mars Helicopter with AeroVironment, Inc. We have Sean Johnson, the thermostat product manager for Toray Advanced Composites. And we have Eric Howard, who is the director of aerospace sales for Toray Advanced Composites. This is an interactive webinar. We do encourage you to ask questions. Depending on the platform you're viewing this, there should be either a question module in the side of your screen or at the bottom. Please submit your question in writing, and we will try to answer as many of them as we can during the Q&A session following the presentations. This webinar is being recorded. This video will be available probably tomorrow. We will try to send the link out to everybody who's watching. Feel free to share it. We will also make the link available on social media channels. And so let's go ahead and get started. Appreciate your patience here. So I'd like to introduce Jim Viola, the President and CEO of HAI.
Thanks, Dan. Well, great. As we get started today, I have to begin by congratulating NASA JPL and the private industry teams that contributed to the first successful controlled flight by a rotorcraft on another planet. I mean, this truly is a milestone in the history of aviation and for all of the rotorcraft community. It is also an indication that the rotorcraft are truly the future of aviation, even here on Earth. A lot of technology that has been developed for space programs has eventually found its way to the commercial sector, and I look forward to seeing the kinds of applications our industry can devise for a helicopter that is capable of flight at 100,000 feet here on Earth. Today's webinar is about the rotor blades on the Mars helicopter and the representatives from the two companies that produce those composite material and design the blades. I think the webinar today is also about pressure. I think the webinar today is going to say that each of those four blades that have to withstand the pressure of spinning at 2,400 revolutions per minute. They have to withstand the incredible temperature fluctuation on Mars. I know people probably have seen those fluctuations and still be able to bite into that thin atmosphere. There also has to be incredible pressure for the two companies joining us today, Toray Advanced Composites and AeroVironment. If their materials and blade design hadn't performed on Mars as it did here on Earth, the whole world would hear about it, and that would be the headline. And the individuals making up the teams at NASA JPL and any other organization that is involved also had to have been under enormous pressure here on Earth. Would this small helicopter fly on Mars as it did on Earth in all the tests? Each of them asking the question, what could go wrong? I cannot begin to imagine the pressure of each of them felt waiting for the results of the first flight to beam back to the Mission Control Center. And I'd really be interested to see how many people watching today on this webinar were watching, depending on your time zone, watching as the stuff downloaded and then was interpreted. Unbelievable. And just as the webinar is about rotor blades and pressure, it's also about planning. Every pilot in the rotorcraft industry understands the pressures of completing a successful flight. The vast number of brilliant women and men who planned and executed this incredible flight thought every what could go wrong question. You got to think through the complete thing and then develop a solution. They trained, they tested, and they tested. And at the end, their flights have been brilliantly successful because they had planned their mission to the point nothing should go wrong. And when a deviation happens, they have a plan for that as well. When a software glitch did slightly delay the first flight, they were already prepared with a solution. It seems to me that we can use the success of the Mars helicopter as an example of what we need to do before every flight. Train and plan for every what could go wrong moment. And if we would just be as successful as the Mars helicopter on all our flights, that would be awesome and safe. So now I turn the presentation over to Ben to get us started with today's presentation on the blades. Over to you, Ben.
All right, well, thank you. Let's see, that set the bar pretty high. Let's see if I can live up to it. Dan, you might need to enable screen sharing.
My apologies. I thought I had enabled screen sharing. There we go. Do need to see your camera as well, please. There we go.
There we go. Got it. All right. Okay, so as Jim said, what we're going to be discussing today is the Ingenuity Mars helicopter. For those of you who aren't aware of this program, Ingenuity is a technology demonstration that flew with the most recent Mars 2020 rover mission. And so it was stowed on the belly pan of the rover, and it recently deployed, and it's been conducting flight tests on Mars. So this was a big team effort. There were a number of industry as well as NASA and JPL team members. I am from AeroVironment. I've worked at AeroVironment now for the last almost 7 years, and I've spent much of that time working on the Mars helicopter program. And so just a very brief background, AeroVironment has been in the business since the 1970s, initially developing human-powered airplanes, actually, for the Kramer Prize. Dr. Paul McCready was the founder of our company. And from there, the company grew into a number of different spaces, high-altitude solar airplanes, a lot of unmanned systems for the Defense Department, as well as commercial systems. But we also have a pretty long history of developing sort of these weird flying vehicles, like flying pterodactyls for the movie industry, robotic hummingbirds for DARPA, and now Mars helicopter for NASA. And so AeroVironment's portion of the program was primarily to design and build the airframe, and that includes the rotor blades, the propulsion motors, swash plates, servos, as well as some of the other auxiliary structures like the landing gear, the warm electronics box. And so this picture up top is the portion of the helicopter that was designed and built by AeroVironment. And then JPL and the NASA centers handled everything else. So all of the systems engineering involved with interfacing with the rover, guidance, navigation, control algorithms, all the simulation, all the testing, avionics development, power system development. It's an enormous amount of work, as I'm sure that you can imagine, to get a helicopter to Mars, much less fly it. So it was an enormous team effort. So why do we want to put a helicopter on Mars in the first place? Right now, there's a number of methods that we have for exploring our solar system. Obviously, the main method is to put satellites around other planets. And so this gives us a lot of information about the surface of the planet. We can get really good wide area maps. The problem with something like this is that surface features aren't particularly well resolved. The pixel size is on the order of 1 meter roughly. On the other end of the spectrum, we have things like landers and rovers. So this would be like Curiosity or Perseverance or Spirit or Opportunity, which are rovers that have been on the surface of Mars over the last 2 decades. And these give us really good surface interaction. We can get really good high resolution images of geological features, but they're very, very slow, and they can't reach some of the really high value science sites like the sides of these cliffs that you can see in this image. And so there's this gap in capability. And we think that that's where helicopters fit in really well. A helicopter can cover a lot of area, can be flying at about 20 meters per second over the ground for minutes at a time. And so it can cover as much area in a couple minutes as a rover might be able to cover in a year, half a year. And so there's a lot of value to having an asset like this on the surface of Mars and on the surface of other planets. However, there's a lot of challenges involved with flying on Mars. First and foremost, Mars is really, really far away. So we're not sitting there joysticking this like you would with a model airplane or something like that. Everything has to happen autonomously, and it has to happen very, very reliably. The helicopter all needs to be self-sufficient, and it has to be very reliable. If anything goes wrong, if a leg doesn't deploy correctly, if a screw comes loose somewhere, that's the end of the mission. It's very similar to manned helicopters in that regard, right? Everything needs to be very, very reliable. The atmosphere on Mars is also extremely thin. It's similar to Earth at about 100,000 feet above the ground. And so as a result, of course, the rotor blades need to be designed to handle that atmosphere. The motors and everything need to be designed to handle it as well. And the atmosphere is also very cold, gets down to about negative 100 degrees Celsius, negative 150 degrees Fahrenheit overnight. However, because the atmosphere is so thin, we don't have any air to cool all of the electronics, the motors, the servos. And so during the day, as we're flying, all of those components heat up very quickly. And that's actually what limits the flight time, is heating in the avionics, the batteries, and the motors. And so the temperature extremes that the helicopter experiences between night and end of a flight are very difficult to design around. And so to test all of these systems and to figure out what we really needed to design for, early on, AeroVironment and JPL began a series of tests using small subscale prototypes in a representative Martian environment. And so you can see that there's some early tests in 2013 where AeroVironment built this little rotor stand. This is really just to prove that you can generate lift in a Martian atmosphere. Of course, the physics says that you can, but there was still a lot of doubt at the time that this would even be possible and that you could build a rotor that would stay together at the high RPM. From here, we moved on to some small scale free flight tests, and we found out a lot of, we found a lot of problems, to be completely frank. Here's one of those early tests. And you can see the helicopter taking off and it's back on the ground already. And in the middle, completely uncontrollable. And this was about as good as we were ever able to do with this little vehicle. And what we realized pretty quickly here is that the flight dynamics in a very thin atmosphere like this are very different than what we have here on Earth. The Lock number is much lower for the rotor, and the ratio of aerodynamic forces to inertial forces is very different. This is more akin to trying to fly a big flywheel that's spinning really fast, but has very, very little aerodynamic forces available to actually try to control that rotor disc. And the damping in the atmosphere is also extremely low. And as a result of this, we realized that we would need to build a very, very rigid rotor system. There's no hinges in this system at all, and a very fast, high bandwidth control system just to maintain even a stable hover. And so taking all of that information that we learned from those early tests, we developed early prototypes of the Ingenuity Mars helicopter. This is essentially the helicopter that's on Mars. The picture that you see on the bottom right is actually the helicopter that's on Mars. It has a 4-foot diameter rotor. It weighs about 4 pounds here on Earth. Mars has 1/3 the gravity, so it's about a third of that on Mars, but it's 1.8 kilograms. And it's powered by a 6-cell lithium-ion battery, which gets recharged by a solar array above the rotor system. One thing that's interesting is that about 60% of the battery is used just to keep the helicopter warm overnight. We only use 10 to 15% of the battery of the power available to actually fly the helicopter during the day. And so one thing that you kind of have to realize here is that in addition to being a helicopter, this has to be a pretty good spacecraft. It has to survive by itself on the surface of Mars. It has to survive rocket launch and everything else. And so designing this to meet both sets of requirements, both as a very reliable and relatively efficient helicopter, as well as a pretty good spacecraft, is very challenging. And so what is a Mars helicopter composed of? Well, the primary structure is basically a carbon fiber tube that acts as the backbone of the vehicle. Onto this, we add 6 servos. So these are servo actuators very similar to what you would have on an RC model airplane, except that, of course, they're designed to handle the temperature extremes and the vacuum of space. You have a swash plate, just like any other helicopter. And this, of course, is what transfers the servo motion into collective and cyclic commands on both rotors. You have a spinning hub and a brushless electric propulsion motor, which drives the rotor blades, and then the rotor blades. And so the whole rotor system of the vehicle looks something like this. This is the primary structural backbone of the helicopter, and then 2 counter-rotating sets of rotors. And onto this rotor system, we add the landing gear, what we call the helicopter warm electronics box, which is just insulation for the batteries and avionics so that we can reduce the power draw that is required to heat those overnight. There's a solar array above the rotors, and then, of course, communications antenna so that we can talk to the helicopter from the Perseverance rover. One of the most challenging aspects, or I guess really one of the main constraints on the size of the helicopter, is accommodation on the Perseverance rover. This is, of course, our ride to Mars, so we want to be able to fit on it. In addition to that, we need to really make sure that we're not impacting the primary mission, which is to search for signs of life on the red planet. And so making sure that the helicopter is extremely clean, everything's built in a clean room, making sure that the number of spores, dormant bacteria essentially, are very, very low. So everything needs to be baked out and sanitized before it goes onto the rover. And also, all of the materials need to be very inert. We don't want to have any outgassing that's going to impact the rover. Any kind of volatiles that come off generally can collect on the lenses of all the cameras and all the optics. And we really don't want that to happen. And so making sure that we have composite materials that are very inert and meet all of the NASA standards is really critical. And getting off of the rover, this is sort of a Swiss watch type of a mechanism or an activity just to get onto the surface of Mars. Down here on the bottom right, you can see kind of how that happens. The legs deploy, the helicopter is rotated to vertical, the other legs deploy, and then the thing is dropped and the rover drives away. This mechanism was developed by Lockheed Martin. And so between the 2 NASA centers, which were developing aspects of this hardware, the end fittings and stuff, AeroVironment, which developed the primary vehicle structure, and Lockheed Martin, which developed the deployment system. This was an enormous task coordinating a lot of engineers to make this happen. And of course, it did. It worked out great. And everything deployed just as we would have hoped. Getting to Mars by itself is an enormous challenge as well. A rocket launch is a really violent event for a poor little fragile helicopter like this. The loads seen by the helicopter are around 60 Gs in all directions, and at very high frequencies as well as very low frequencies. And so all of the primary loads on the helicopter, with the exception of centrifugal force on the rotor blades, all of the load cases that we have to design for really come from this launch event. This is a very, very high stress environment for the helicopter. And in addition to that, there's a lot of high shock events as pyrotechnic actuators are being fired during both the entry, descent, and landing onto Mars, as well as getting the helicopter off of the rover. There's a lot of pyrotechnic cutters that are involved in that. And so, of course, in addition to being a spacecraft, the helicopter has to fly and has to do it fairly efficiently. And so the rotor blades were developed here at AeroVironment using in-house design codes. and using a lot of information that we got from developing high altitude solar aircraft, high altitude pseudo satellites, as we call them. The highest airplane that we've developed flew at 96,000 feet. And so the atmosphere is actually fairly similar on Mars and on Earth at about 96,000 feet. And so we were able to pull some of that data in to develop these rotor blades. It's about a 4-foot diameter rotor. The rotor speed on Mars, what we're flying right now, is 2,538 RPM, which is about the same as a helicopter, like a model helicopter here on Earth. But of course, we're much, much lighter, and our chord is much larger. The solidity of these rotors is very high, and that's to account for the very low density. The aerodynamic regime that we're flying in, though, is very strange. The chord Reynolds number for these rotor blades is around 10,000. And so the characteristic aerodynamics are pretty similar to a monarch butterfly here on Earth. That's a very low Reynolds number. It's kind of like a rubber band powered indoor model airplane. But the tip Mach number is very high. As we're flying, it's about Mach 0.7. The design tip Mach number is 0.76. And so we do attempt to avoid compressibility issues just through airfoil design. And so far, it appears that that is the case. We don't have any evidence that we're hitting any kind of a drag divergence Mach number. But it's going to depend significantly on the actual density that we're flying in. One of the main constraints on the rotor design, though, as I mentioned earlier, we have to build this to be very, very rigid just to be controllable because the Mach number is so low. And that really impacts the design significantly. We try to design for 2 per rev, and we hit about that, depending on the frequency that we're flying at, or the operating frequency. And that drives a lot of the structural design of the entire helicopter, but especially the rotor blades. The outboard sections of the rotor blades are using these very thin 5% thick airfoils, which at this Reynolds number actually are a little too thick. We want those to be thinner. We can't do that because of the structural design constraints. And the twist of the rotor blades is, the taper of the rotor blades is similar. To hit that very high flap frequency, we want pretty high taper. There's about 16 degrees of twist in the rotors, which is very high relative to a lot of helicopters. And the reason for that is that this is a hover optimized case. We don't really care too much about flying in forward flight very fast, but in hover, we want to be very efficient. Those rotor blades are driven by brushless propulsion motor. These were designed in-house at AeroVironment. And you can see it here. It looks pretty similar to what you would have on a drone here on Earth, or a helicopter, like a model helicopter, except that they're very efficient and they need to store all of the heat almost adiabatically. And so at the center of this, you can see there's this kind of oddly shaped structure. It's a little bit yellowish. That's actually a material called albumet. It's a beryllium alloy, and that has a very high specific heat. The rotors are controlled by a servo and swash plate mechanism. You can see those here. This, again, pretty similar to what you would have on any Earth-based helicopters, except that they have to be very dust resistant. They have to be they have to operate across a very wide temperature range, and they have to handle all of the UV radiation, the radiation environment on the electronics, and have very low outgassing as well. And of course, structural design is absolutely critical. We don't want the helicopter to break before we can fly it. And so there was a lot of effort put into analysis on the helicopter structure, as well as testing. And there were a number of tests on various test vehicles, as well as the final flight hardware to simulate the launch environment before the helicopter was ever even stuck on the rocket. And a really critical aspect of this is composite fabrication. Advanced composites are absolutely required to do a mission like this because the mass constraints and the strength requirements are just very, very difficult to meet with conventional materials. And so getting materials that meet all of these very high stiffness, very high specific strength, very low density, as well as surviving the space environment, so radiation, micro cracking, outgassing, so volatile chemicals coming off of it, and the temperature range that we need to fly at was absolutely critical. And Toray Advanced Composites developed those materials and supplied those materials. And so Sean is now going to be talking about that process to develop those materials.
Sean, you're muted still.
Thank you, Ben. Let me get my screen up here. Okay. So first of all, I'd like to really thank AeroVironment and Ben and NASA, JPL for the chance to work with them on this project. It's been, pardon me, very exciting. All of these projects are something that we have a good amount of heritage on, and a lot of experience, and we'll talk about those hooks back into what Ben and AeroVironment have been doing as we walk through the presentation here. We do understand that many of you may not be, sorry. Okay, many of you may not be entirely familiar with Toray Advanced Composites and what we do. So we'll give you just a very brief introduction to our company. Sorry, having a little trouble advancing the slides. Okay, Toray as a group is a very large company. It's over 100 years old. It's founded in 1926, and it has over 200 operating subsidiaries, of which Toray Advanced Composites is one. We are based in the carbon fiber and composites business division. And in the United States, we have a very substantial presence. Toray Advanced Composites is based in California, Northern California. You can see the units there. Fairfield and Morgan Hill comprise that. We have a sister division, Composite Materials America, CMA, that's based in Tacoma, Washington. They provide the prepregs for the 787 and 777 aircraft. In Decatur, Alabama, are where the fibers, the Toray fibers that we use are made for the standard and intermediate modulus fibers. And we have a super site in Spartanburg that actually makes the precursor for the fibers and prepreg. Toray Advanced Composites has three main business areas that we emphasize, and our customer base is highly diverse, whereas our sister division is very commercial aircraft centric. We are a little less than half in aerostructures of many various customers. And then we have the space and communications, a lot of satellite launcher, that type of work. And then we also have high-end industrial and sporting goods. Very interesting, as Ben had noted, the Ingenuity Mars helicopter is as much a spacecraft as a helicopter. So we have experience in both of those areas, and we were able to bring that to bear to help with that project. As I noted a second ago, we are headquartered in Morgan Hill. We have 6 global production sites, and we've been supplying thermoset and thermoplastic composites for over 25 years. For For some of you that are a little further up on the age scale, you might remember Bright Composites and YLA Composites. And we are the heritage that became Tenkata, which is now Toray Advanced Composites. We are a very key supplier to the established and emerging new space markets, aviation, rotorcraft, UAV, urban air mobility, which again are very helicopter type derivatives. That's one of our key areas and an area that we're going to be supporting very heavily throughout the future. So what we actually make are thermoset prepregs, thermoplastic prepregs. And what that is very precise application of our proprietary resin systems to a reinforcement. These can be collimated unidirectional fibers, like in the picture in the center bottom there, or to woven fabrics, much like you see on the bottom right-hand side of the screen. We also make adhesives and film adhesives and surfacing films that are made to be compatible with our products. We make molding compounds that are precision. They're made for matched metal precision molded parts, like you see in the middle of the right-hand side there. And then these prepregs feed back into the parts that you saw Ben demonstrating in his presentation. We are a key provider for almost every military and commercial satellite in the Western world. And really that heritage based on our satellite work is what has enabled us to be a good partner, we think, to AeroVironment and NASA JPL to participate in the Mars programs and the Ingenuity Mars helicopter. We've worked with all the old space and new space companies, you know, all the Lockheeds, folks like SpaceX, Blue Origin, Firefly, Rocket Lab. All of those companies are ones that we have had association with. Now to talk about, this is really the tie-in with what Ben was talking about, the design considerations for space materials, which again, in the case of the Ingenuity Mars helicopter, are really more space materials than they are materials for aeronautics on Earth. The aspects that the design aspects you see in red on the left are much more geared to launchers, but the dark blue aspects you see in the middle and then the green on the right are all key aspects of what has to be considered when you're talking about a satellite and something, again, like the Mars rover or the Ingenuity Mars helicopter. As Ben noted, the low outgassing is extremely important. You go a long, long way to Mars, or you go a long, long way to the edge of the solar system. And if you basically have materials that spray out gas, the cold of space condenses the volatiles onto the lenses and the sensors, and you can end up going a very long ways to accomplish nothing. And in the early days of satellite space flight, that was shown to be an extremely critical parameter. And basically just the adhesives that were used to hold things together. In the early days, a lot of those were metal, and just the outgassing from the adhesive could cloud the optics and the sensors. Another extremely critical aspect that Ben had mentioned was micro cracking. When materials, especially composites, thermal cycle, there's a tendency, or there's a tendency that you have to fight that will cause the matrix to generate small cracks. And these can run through the thickness. These can run along the ply interfaces. And what happens is a net result. They may not be catastrophic on their own, But what will happen is there's a relaxation. So effectively, you will end up with a lower stiffness structure when you have micro cracks present. And to the extent you have more and more micro cracks, it would become more and more relaxed. And as Ben was noting during his presentation, those are very, very tight constraints that the Mars helicopter Ingenuity has to operate under. And it's so finely tuned that if it lost a lot of stiffness and gain compliance, it would be a very difficult thing for that. And kind of underlying micro crack resistance is the thermal cycle performance, the coefficient of thermal expansion and moisture expansion. All composites absorb some moisture, and that's why these materials that were selected are actually very key. They absorb very little moisture, hence they have very little moisture expansion. And a lot of these materials too are very, very low CTE, close to zero, over the types of temperature ranges that Ben was describing in his presentation. The other thing, again, if we move over to the right-hand column, we want the ability to take these materials and make, thick structures, thin structures, sandwich structures, tubes, struts, flat, thin panels. So that's a very, very large consideration. And really not least of which is the heritage in the database. The materials that are used in the Mars 2020 mission have a very long space heritage and a very long history of success. And of course, the properties, laminate properties. A lot of these materials have to be ultra stiff and ultra strong in relation to conventional engineering materials. So in terms of the Mars 2020 mission, we actually have materials really all over it. The Mars spacecraft heat shield was our materials. It's manufactured by Lockheed Martin Denver, who is a very, very good customer of ours and who has a lot of familiarity with our materials. BTCY1 is a 180C curing cyanide ester. And again, that reflects a lot of those properties we looked at. High, low CTE, low CME, high resistance to micro cracks, very low outgassing, high resistance to radiation. And it has very good resistance to heat, high heat, as you would see in the heat shield, or some of the electronics areas that it might be used in or protecting in areas like the heat shield or the Perseverance rover. These materials are also extremely good for dielectric performance. So if you have reflector surfaces or areas that you need, conversely, where you need high dielectric transmissivity and very low loss, we put those with things like astroquartz, which are used for terrestrial radomes, high performance radomes, and they find equally good application in space. I'd mentioned some of the complementary products in the earlier. In this case, there's a cyanide ester adhesive that's very well tuned to work with the BTCY1. That is its complement. And then, of course, the star of the show, the Ingenuity Mars helicopter. A whole suite of materials there that were used to do the composite work. You probably noticed on Ben's pictures of the blades, they're shiny, of course, so they have very good surface and contributes to lower drag and lower loss, aerodynamic loss. Also very, very thin, very thin plies, so you can balance the stresses within the laminates. And you probably noticed that the surface looked like it was a series of squares, and that's the spread fabric with the high modulus fiber that you saw. T300 1K plain weave fabric, that's a very fine weave fabric that actually is fairly conformable and is good for things like doublers and hubs and the like there. The M55 tape is a very, very high modulus material. And it's made into a tape that's only 2.5 milli-inches thick. So you can ply those up very, very thick. I'm sorry, very, very thin with a large number of plies to get balanced laminates and reduce your internal stresses in the laminates. So again, basically the rationale for these materials are space heritage, low CT and outgassing, high micro crack resistance, and high strength and stiffness. We actually have a very large amount of Mars experience. It's almost like TAC or Martians in a way. We've been on all the rovers and landers, and with various of the prepregs, including BTC Y1, EX1515, and another one of our cyanate esters that's a very tough one, RS3. I like this picture because this basically shows you how these materials are used in a satellite. But if you reconfigure these, you see where they're used in the rover and the Ingenuity helicopter. Things like the solar arrays, large flat panels, are used, for body panels or optical benches or things like that, solar array surfaces. Then you have things like booms, trusses, and yokes that are, round tubes, square tubes, have to be very stiff, resist deflection. You have other areas that have to be very, very stiff and very low CTE for the optics and the communications areas. So this is very interesting in that, again, you can see how all these components really play into where the individual uses lie on the Mars helicopter and the rovers. We do have quite a lot of terrestrial experience as well. We have materials on structural materials on the Apache, nothing on the blades, but we also have worked with Ericsson Air Crane. We have epoxy material there that's used on the blades there. The Leonardo copter, formerly Marenco Swiss helicopter, uses one of our epoxies and carbon fabric on various parts of the structure. And then one of the new UAM companies that we work with, Joby, again, some of those vehicles look amazingly like very fancy helicopters. And so, again, it makes sense that a lot of these materials would find a home there for use. I won't dwell on this, but this is a list of our key resin materials and why they're useful in space. The ones in red are the Martian materials, as I like to say. The EX1515, the BTC Y1, and the RS3 and 3C. I'm not going to go into a ton of detail on this chart, but the three lobes are the kind of carbon fibers that are typically find a home and use for spacecraft. If you look at that lobe that's on the lower left, those are standard modulus fibers, and the implication there is they're the lower stiffness group, but they actually still have stiffnesses that approximate, actually higher than steel, and they actually have strengths that are on the order of 2 to 3 times the order of high tensile steel. If you look at the top center lobe, those fibers actually have 1 to 1.5 or slightly more times the stiffness of steel, and they have 5 times the strength of high tensile steel. And the lobe on the right there has stiffnesses up to and over 3 times that of steel, and strengths that are up to 3 times that of tensile steel, high tensile steel. And the reason to show that again is to kind of emphasize what Ben was trying to show, in that these are very, very specialized structures, and they really, really need materials that are not like our traditional engineering materials, and they really are very mission enabling in that sense. And I'll just wrap up by saying, we're again very proud of our work with AeroVironment and JPL. We have done a lot of work where we understand a lot of these very multi-tiered efforts, where we participated in efforts that have up to 5 layers of suppliers and relationships. We have a huge amount of experience in the satellite area, and probably not going to have a helicopter on Pluto, but we do have materials now that have actually, composite materials from Toray Advanced Composites that have actually left the solar system and are flying on new horizons beyond the orbit of Pluto. So I thank you everybody for your attention, and I will turn it back to Ben. He had some really great pictures that he's going to share with us.
Sure, thanks, Sean. So I'll do this fairly quickly. I think we're starting to run out of time, but I wanted to show just kind of a slideshow here of pictures that I'll run through. Of the fabrication process, as well as some of the pictures from the surface, and I'll step through what's going on in them and talk about what we're doing now. So as I said, a lot of the airframe hardware was fabricated at AeroVironment. We stood up a clean room facility specifically for this program, and you can see one of the design engineers, Sarah, holding some of the hardware. Something that's a little unique about AeroVironment is that essentially all of the engineers, at least on this program, built their own hardware, with the exception of some of the machined components. So there's a very, very strong connection between fabrication process and design, which I think is really critical for an engineering program like this. After fabrication, the helicopter was integrated in Jpl Clean Rooms. And so here's kind of a slideshow of some of those facilities. You can see the helicopter going through some tests. On the bottom left is the helicopter as it's arriving to the clean room facility. And then it goes through environmental testing. So JPL has a number of really specialized facilities that are, some of them are designated National Historic Landmarks that protect them, just to test spacecraft like this. And it's a really critical attribute of working with JPL and NASA, is that the helicopter is able to go through essentially all of the environments that it was ever going to see on Mars prior to ever being launched. And so this is looking at some of the thermal vacuum chambers, the shaker table at the top right that simulates the launch environment. And then on the bottom right, you can see the helicopter as it's being mounted onto the belly pan of the rover. In addition to the environmental testing, there was quite a bit of flight testing. There were several hundred simulated flights that occurred in this space simulator chamber over at JPL. You can see it in the far right with the Curiosity rover actually going through testing. This is a pretty special facility. You can see in the back of this picture in the middle here, there's all these fins, and those are actually radiator fins. They have like 1-inch diameter tubes that run through them that liquid nitrogen can be run through. And so this facility can be taken down to essentially almost absolute zero, as well as simulating up to 2 suns of solar influx at the test center at the bottom here. And they can do that simultaneously. It goes through about an 18-wheeler of liquid nitrogen every 6 hours or something like that. But really a very special facility, and that helped us with flight testing quite a bit. And here's one of the videos of one of those flight tests. So in the top left, you can see the view that the helicopter has, and that's what's being used for navigation. On the ground, you see all these little tape X's, and those are just to simulate rocks on Mars. You can't just have a bare white floor the helicopter doesn't know what it's looking at. But this is simulating a flight on Mars in a representative atmosphere with all of the onboard navigation being used to actually control the helicopter. So after testing, final integration occurred at Kennedy Space Center. So here you can see Chris, one of the JPL's mechanical engineers, very, very carefully loading the spacecraft onto the belly pan of the rover. And on the right, you can see it prior to being closed out with the dust shield. And here's what that looks like when the rover is integrated into the back shell. And this is the configuration that the rover and the helicopter are in as they fly to Mars. And you can see circled in red on the left before the dust cover was installed, and on the right, it's just after. And so during entry, descent, and landing onto Mars, after the heat shield is jettisoned, the helicopter is actually the first thing through the atmosphere. And so if anything had gone wrong, the helicopter would have been the first thing to arrive on the red planet on the surface, obviously immediately followed by everything else pancaked into a crater. But kind of interesting that was the first thing through the atmosphere. And so the helicopter and Perseverance and Mars 2020 spacecraft were launched July of last year, landed on February 18th, and at present we're operating on the surface. And so we have some great pictures of the helicopter as it's going through the deployment sequence. This is taken by the rover during that process. So here you can see it stowed just after the dust cover was deployed. One of the locks is released, the helicopter begins to rotate down. It rotates fully vertical and the legs are deployed. And then the helicopter was deployed onto the surface. And so this is one of the first pictures that we get of that. One thing that's interesting to note is that even though we had a dust cover, there was a little bit of a gap in a few areas around that dust cover. And during landing, a lot of dust actually just came straight in through that gap, got into the mechanisms, and as we deployed, it was all dumped right onto the solar array. So a little bit of a lesson learned there for the whole team. You know, there's actually a lot more dust during these landing events than we would have expected. Didn't cause an issue. We still have almost full power out of the solar array, and actually after the first flight, all of that dust was removed. So it is self-cleaning. And here is one of the more recent flights. Skip ahead here a little bit. This is the helicopter taking off and flying on Mars. This is taken by the rover from about 60 meters away. You can see it takes off, it hovers. This is at 5 meters above the ground, and then begins to translate. And so this was the third flight, and it's going to translate off screen. I'll skip ahead. And it goes down 50 meters downwind, and then it comes back up, and it's just going to land again. And this was the first checkout flight testing forward flight of the helicopter, and then comes down and of course lands. So a relatively uneventful kind of a flight, but of course, when it's 160 million miles away, every second of that is very stressful for the whole operations team. So with that, I think we'll open it up to questions, or I'll hand it back over to Dan, I guess.
Okay, let's see, there we go. Okay, I'd like to invite Sean and Eric to go ahead and bring your cameras back up. I did check, apparently NASA, according to NASA's website, the helicopter did not fly today. They are doing some evaluations, and they do plan to try again on the fourth flight again tomorrow. So we'll keep our fingers crossed for that. So, gosh, I can't tell you how much I appreciated the presentation already. It's been fascinating to see the whole process. Actually, I'm curious for both of you. Both companies seem like you have a good relationship with JPL and with NASA. And so what was the first kind of reaction your companies had when they said, hey, we want to fly a helicopter on Mars. Can you help us out? Eric, maybe, or Sean, you want to start out with that? I don't know, maybe this is a chicken and egg type question too. I don't know where the process began. Did it start with AeroVironment and you guys went to Toray for the composites, or did somebody come to Toray first and say, we need blades for this, and then it went to AeroVironment? So maybe I'll let whoever started first go.
Yeah, I'll take that, Dan. Thank you very much, and thank you, Sean and Ben, for helping to put the presentation together. I remember quite vividly when Ben and the AeroVironment and JPL teams reached out and called me on this. Yes, we've got a great relationship with JPL and AeroVironment, and are flying on some of their other high altitude polar planes. And when they said that they were going to be putting a helicopter on Mars, I think my jaw probably hit the floor. And it's certainly AeroVironment's design, but the key considerations that have been discussed here were so essential. The materials that go up into the space environment, we talked about outgassing, and they act like a sponge. And so having materials that have low moisture absorption, that equates to low moisture desorption in a vacuum environment in space, and combined with high stiffness and low CTE, our portfolio and heritage really, I think, fit what they needed, and it was a good relationship. And gosh, that goes back probably over 5 years now. And so it's exciting to see the success on the Red Planet, and we've just been appreciative to be a part of it. And really, all the credit goes to Ben and his team.
Ben, did you want to add anything there?
Yeah, sure. So, I mean, I think similar to Eric, AeroVironment had been involved with some very early proposal efforts in the 90s on developing a helicopter to go to Mars with JPL, with Bob Ballaram, who's the chief engineer over there. But, when they came back to us in 2012, I wasn't at the company at the time. I joined in 2014 to work on this program. But, I think that it was something that excited a lot of people. It's sort of like the ultimate unmanned aircraft development project, and obviously there's only one of them. It's from a business point of view, it's not great, but from an engineering point of view, to the whole technical staff, everybody's extremely excited about it, and so I think that it was kind of a big honor that we got to work on this at all, that we were able to collaborate with JPL on it, and so having a pretty major impact on the design, has really been great. I think it's been a really, really good teaming effort. AeroVironment, JPL, NASA, Toray, and all the other industry partners, I think, have worked really well together. So yeah, it's been a great effort.
I'm glad to hear that. So let's get into some of the questions. I think it seems like the majority of these will probably be for you, Ben. We'll make sure that we try to split things around. What are some of the key adaptations that had to be made to the design of the rotor blades for operation in the low Reynolds number environment?
Yeah, sure. So the low Reynolds number environment, my background is actually in more low Reynolds number aerodynamics, and same with a lot of the team, same with a lot of AeroVironment in general. We do small unmanned systems like this. This is very low Reynolds number aerodynamics. As you get down below about 50,000, it's more, it's kind of like you're swimming through honey more than anything in a lot of ways. The main thing that is important there is to have extremely thin rotor blades. Typically, we would use 2% thick airfoil or something like that. In this case, we really can't do that just because of the structural reasons. And so trying to design an airfoil that still had good performance, but still has a reasonable amount of thickness, these are 5% thick airfoils, was fairly challenging. But, these airfoils are adapted from the high altitude propeller airfoils that were developed on Helios on that program. And so we had a little bit of a baseline to work from.
Okay, question for Sean or Eric. The temperatures, the aircraft, and obviously I think you may have addressed this a little bit with the fact that you do work with satellites and other craft that are going beyond the solar system now. Outer space is around over 400 degrees below zero, or below zero Fahrenheit. The composite materials, how much of a concern, or how do you adapt your materials to handle extreme temperatures like that? And did the Mars helicopter, was it ever exposed to those temperatures when it was traveling over to Mars?
I'll let Ben handle the exposure temperatures. What I will say is our space materials are in a way happy accidents for most of these, in that they just have this tremendous balance of properties, that suits them well for space. A lot of the geo satellites, for instance, will routinely cycle from bright sunlight to absolute darkness of space, and they'll go from minus 180 to plus 180 C. And then the James Webb Space Telescope that we have a lot of material on, is going to be operating down near 4 degrees Kelvin. So those materials actually function very well. It's a combination of toughness, microcrack resistance, low thermal expansion coefficients, and as Eric touched on a bit earlier too, very, very low moisture absorption, so you don't have a lot of moisture distortion coming into the materials. That being said, we have also been developing specifically materials for cryogenic use as well, that are a little more budget friendly, I'd say, to some of these things. The thing with a premium material is they usually come with a bit of a premium price, and you can't build gigantic LH2 and LOX tanks out of things that are generally the types of materials we're building rovers and Mars helicopters out of.
Ben, did you want to address the exposure question?
Yeah, sure. So yeah, the temperature range that the helicopter has to operate through is very high. Obviously on Mars, it gets very cold, negative 150 Fahrenheit or so. During transit to Mars, everything is fairly, in our case, everything is fairly evenly heated, but it's still negative 80 degrees Celsius, which is not particularly warm. But the thing is that it doesn't have to thermal cycle too much. Like a satellite orbiting Earth, for example, goes in and out of the Earth's shadow. In our case, we don't do that during transit. However, one thing that I really hadn't mentioned, a lot of what we have to do to clean the helicopter is going through bakeouts. And so the helicopter is put into essentially an oven in a vacuum for 72 hours or something. And so the hottest that a lot of the components ever get is during that time. And so the temperature range that it has to operate over is about 400 degrees Fahrenheit.
Okay, question, what are the cone-shaped bumps on the insides of the rotors?
Yeah, I should really just make a slide on that. Everybody always asks it. So those are Chinese weights. The loads that the servos have to react, aerodynamic forces actually are not very significant in this case. The pitching moment of the rotor blades, that's only about 5% of the total maximum control force that the servos have to react. The rest of it comes from the inertial loads. As you're spinning these blades at 2,500 RPM, you're moving them essentially at 1 or 2 per rev. Those inertial loads on the servos are very high. In addition, you have a centrifugal moment, which is the propeller moment or tennis racket effect, where the rotor blades are trying to flatten themselves out. They're trying to essentially de-pitch themselves. And you see this on helicopter tail rotors quite a bit, or constant speed aircraft propellers. If you add an inertial counterweight, you can reduce that moment by essentially making the properties of inertia more constant. Rather than having a line of mass, you can make it more symmetric. And so that's what those little cones are. There's a tungsten ball on the tip of them, and they reduce the circuit load.
Okay, from Alistair in the UK, what is the stalling angle for the blades on Ingenuity?
It's around 17 degrees at 75% radial location. We fly at about 9 to 10 degrees at 3/4 chord or 3/4 radius. And we really don't ever want to command above about 14, 15 degrees. But yeah, it's about 17 degrees in standard flight.
And we've had this from a couple different people. Are there erosion strips on the leading edge of the blades, or is there any kind of erosion control built into it?
There is not, and it was a concern, and it still is a concern. The helicopter is baseline for 5 flights only, and so if we were going to fly longer, then absolutely we would need to pay a lot of attention to that. What we did was, NASA Ames put together some pretty fancy CFD models looking at how the particles will disperse in the atmosphere as we're taking off and landing. We don't get into re-ingesting the particles. Essentially, they come down and out, and they don't get re-ingested back into the rotors. And if you watch the videos, there's not much of a dust cloud. You can see a little bit, but it hasn't really been a problem for us.
So it's very similar to the rotor system that's on a Ka-32 or something like that, where a traditional helicopter, an older helicopter from the 70s, 60s, 70s design model.
Right.
Okay. This might be a question more for NASA JPL. I don't know if you guys would be able to answer this. How were the local prevailing winds determined for the flights? So was that something that was tested for? And does the rover act as a weather station for the Ingenuity helicopter?
Yeah, so that's the trick. Until Perseverance, we really never had a weather or a direct wind measurement on the surface of Mars. What we were using was a large, there's a number of university groups that are trying to model the atmosphere on Mars, and they're doing this with large eddy simulations. The kind of nice thing about the weather on Mars, there are no oceans, there are no bodies of water. And so it's fairly deterministic how those wind patterns are going to emerge. We fly early enough in the day that convection isn't too much of a problem. There aren't big thermals or anything. And so it's designed for 10 meters per second of wind. And what we've been seeing from the wind sensor that is on Perseverance is that we've been flying at about 4 meters per second steady with gusts of about 6 meters per second. And so that's almost exactly what was expected from the large eddy simulation. It's really impressive.
And I'm not sure if this is for Toray or AeroVironment. What was the molding method for the blades? Are they hollow for weight?
Yeah, so the rotor blades are actually foam core. It's got a Roacell foam core, which was machined essentially net to the molds, and then it's aluminum tooling. And so, yeah, it's very thin composites over Roacell cores.
Here's a question for Sean or Eric. The materials, are there any biomedical uses for your materials?
Yeah, we do have some orthotics customers. We do not do implantation biomedical applications, though.
Okay. How is the, and this will be back for Ben, how has the blade design on this mission been able to elucidate any new blade design for Earth, especially for new aircraft like Joby?
Yeah, well, so I think that, the materials are really pretty enabling for a lot of what we do here on Earth. The Reynolds number on Mars is much lower than what we would see here on Earth. So the airfoil design, for example, would be very different. For the high altitude airplanes, high altitude pseudo satellite kind of solar aircraft, this is absolutely, it's a kind of, it follows directly from the work that has been done on that previously, and this will flow into the future work. That's already happening. But yeah, I think that material properties that were developed for this kind of an application, that's really enabling for a lot of earth-based applications too.
Okay, somebody's asking if there's any place that they know that you know of where they could see a geometrical design of the blade. Is that something that NASA might have, or JPL, or you folks might have that is available?
Yeah, so JPL has released some form of a CAD model, and I think it is fairly representative of the rotor blades. It's the actual rotor blade design, would have to come from JPL. I believe that it's EAR controlled. It shouldn't be ITAR, but it would have to come from JPL. So I can't send it out, but there is a model online that you can download.
Did you have to conduct any static balancing for the blades?
Yeah, so we actually also did dynamic balancing at one point. It wasn't particularly meaningful, I don't think, to statically balance or to dynamically balance them in the configuration, at least that we were doing, just because the rotor system was extremely rigid, and for the counter-rotating coax helicopter, that's very difficult to do. What we did end up doing is statically balancing the rotor blades, as well as trying to match the inertia and trying to match the center of mass. And that, it turned out, was totally acceptable to get the vibrations low enough that the IMUs could handle it no problem.
By the way, I realize we are about 10 after the hour, 12 after the hour. Are you folks okay with staying a little bit longer? A few more of the questions? The questions have kind of exploded. So some of them have things you've
I'm
already
fine.
appreciate that.
Yeah, we're fine.
Are there any surprises in the way the helicopter flies or handles?
So there were surprises early on in testing. There aren't a whole lot of surprises from Mars. It almost, looking at the simulations beforehand, the aerodynamic performance and the power requirements and servo inputs, and comparing it to the actual flights, it matches very, very closely. It's actually really impressive. And the reason, of course, is that there was a lot of time and effort put into validating those simulations using hundreds of performance tests on a lot of different types of test rigs, gimbals, a tether offset that we could fly freely, multiple axes that we could control or lock out so that we could isolate specific behaviors. And so that was really critical in getting that simulation to pretty much exactly match what we see on Mars.
This question might be for both of you, because I could see where the composition of the material, blade material, might be affected too. Does having a CO2 atmosphere instead of a nitrogen oxygen atmosphere affect performance and design? Sean, Eric, you want to address that for your composites?
The short answer for the material is CO2 is very inert against cyanide esters. So from the resin affectation point of view, it has no real degradation or any effect.
And normally for space missions, highly oxygenated environments is a concern for flammability and resistance in that area, especially when you're talking about manned missions. But for this, CO2 is not a problem.
And then Ben, what about from the AeroVironment side?
Yeah, so there isn't too much of a difference really in operating in CO2. One of the kind of interesting things from a materials side is that oxidation on a lot of the components doesn't occur very quickly. And so things like galling, for example, are fairly different in a CO2, very low density CO2 environment. In addition, the environment on Mars is there's very little moisture in the atmosphere. The humidity can be very high. Well, the relative humidity can be very high, but the actual amount of water vapor in that atmosphere is very low. And so lubricants, for example, act very differently. Friction can vary wildly. Graphite, which is a pretty good lubricant here on Earth, is extremely abrasive on Mars in that atmosphere. And conversely, moly disulfide, which is fairly poor lubricant by itself on Earth, is really, really good on Mars. So it does change the materials, but it's not significant for how the aircraft flies or anything like that.
During the early design and testing, did you face any instability issues like resonance? And if so, was it due to the flexible blades?
Yeah, so resonance is exactly why the whole rotor system was built to be very, very rigid. And it's not just the rotor blades. I mean, that's a big portion of it. The reason that the rotor system is so rigid, one of the main reasons anyway, is to get the regressive flat mode to a high enough frequency that is outside of the range that's observable to the flight controls. And so getting all of those first natural frequencies very high was absolutely critical because the damping in that atmosphere is so low. And same thing with the landing gear, for example. We pushed the first frequency of the landing gear outside of the operating range of the helicopter, the solar array, the primary structure, the mast. And yes, there were a lot of resonance issues on test stands. If you look up pictures of the test stands that were used for this, they're these gigantic, 12-inch by 12-inch aluminum beams. And that's exactly for that reason, to get those resonant modes way outside of, even the 4 per rev excitation frequencies that we get from the helicopter.
Okay, are there wind speed limits for the helicopter?
Yeah, 10 meters per second is what it was designed for. It was tested up to 12 meters per second, essentially with a big wall of computer fans. It's about 5,000 computer fans that were run sort of as a pseudo wind tunnel in the space simulator. Beyond that, I think the answer is there are no guarantees. It's not going to immediately crash if it gets a big gust like that. But to handle higher flight speed or higher winds, you'd probably want to have a direct measurement of what that wind is. We're just looking at the ground. We don't have an airspeed sensor. And you would want to do gain scheduling based on that.
Are the blades fixed pitch?
No, they're collective pitch and cyclic as well.
Does the helicopter experience effective transitional lift?
Yeah, well, so yes, we're controlling altitude with a laser altimeter, so it's closed loop. We can't directly see that, but we can definitely see the power required to fly decreases with wind and with flight speed, which is exactly what you would expect, right? So yes.
And actually, I misspoke. That was effective translational lift.
Yeah, that's
okay.
Yeah, that's what I figured.
Is there going to be an issue if one of the rotors is RPM controlled instead of pitch controlled?
Issues, yes. So one of the main problems here is that the inertial forces and the gyroscopic forces are very large relative to the aerodynamic forces. And so if you have a net angular momentum that is not zero and you try to give it a pitch command, there's going to be cross coupling into a roll axis, for example, which is going to be dependent on what that mismatch in RPM is. And so that's why we were very careful to essentially lock the rotor RPM, and lock the net angular momentum on the vehicle to be effectively zero.
Is Toray Advanced Composites and AeroVironment involved in the NASA Dragonfly project mission?
We are
Good
not.
question.
Yeah, we are not
Likely-
right now.
Likely Toray is.
Okay.
I know a lot of the same people, but no, we are not directly involved.
Ben, I think I think you might have addressed this already, but somebody's asking again, what is the lock number on the blade?
It's 0.4, roughly. It's around 0.4, which is pretty low.
Okay, I think we've got through the most of the technical questions for the blade side. There's a couple of other real quick ones that we'll see if we can answer. What is the approximate weight of the custom Bldc motor?
Yeah, so it's built into the structure, but the stator is around 55 grams. The whole thing is around 78 grams, including 17 grams for the motor driver, which is co-located with the motors. So it's around 78 grams per motor.
And what type of bearings were used on the rotor hub for rotation over the mast and for blade pitching?
Yeah, so it's all full ceramic. So silicon nitride, rolling elements and races. That was done primarily for mass reasons, but also to match the very low coefficient of thermal expansion from the composites. And so using those two materials in combination worked really well. And it really reduced the mass quite a bit. There's a lot of weight in the steel bearings.
Why did you choose fabrics for the blade material reinforcement form factor? Sean showed unidirectional materials, which would have been less fiber undulation and increased stiffness, correct?
Yeah, so I'll answer that first, and then Sean or Eric can if they want. So we use unidirectional fibers for the spar caps. So in pure bending, or not pure bending, in tension and compression, unidirectional fibers are great. Off axis, obviously, they're not. The material that you're seeing on the rotor blades is a spread toe woven material. And so that kinking in the fibers is significantly lower than it would be in like a plain weave or something like that. It's very, very similar to just having two plies of unidirectional that are laminated on top of one another. In our case, we need to have torsional rigidity in the rotor blades. And so we have to have bidirectional material at 45 degrees kind of to the chord line of the blade. And so that spread toe, very thin spread toe material works really well for that. Unidirectional is used on the caps where we only have kind of single directional loads.
And I'll add to that a little bit. And the aerial weight of that particular fabric is very low. And so combined with the spread fabric and low aerial weight, the crimp angle really isn't much of a contributor.
Yeah, and one other deal, again, it's all related back to the crimp angle too, that's so low on the spread toe. You actually get significantly better compression strength than you would from a ropey kind of a round section toe. So the mechanical properties are helped quite a bit by that.
And as a guy who had to build the blades, I'd much prefer to do it out of a woven material.
Yeah,
I've done it out of very, very thin unidirectional materials before, and it's not fun.
It's less drapey, and it's
yeah.
I guess this one might be for Ben. What is the biggest challenge or design reiteration that you experienced?
So, designing this thing to fit on the rover, it's not something that we were really paying a whole lot of attention to initially. There was kind of a spot that was being held on the rover for the helicopter. And I think that essentially what happened is that nobody thought that the helicopter was actually going to fly on Mars. And that space quickly was used up for something else. And so, when we kind of went back to the rover guys and said, hey, we're ready to start integration, all of a sudden we had to kind of figure out what exactly that meant. And, in addition to that, we hadn't really planned for all of these launch loads properly, how to hold the helicopter. That's not a simple thing, right? It's a very, very brittle piece of hardware. It's very stiff, but it's, it has to be very light. And so compared to the 1,200-pound rover, it's a pretty brittle little piece of delicate hardware. So that took a lot of work, and there was a lot of redesign based on that.
Okay, guys, yeah, it's almost 5:30. We have a whole bunch of questions that we just did not have time to get to. So I'm going to finish up with one last question. I got to go back and find it here again real quick. Basically, for each of you, what was the coolest moment for you in this whole project? You know, the testing, the development, just being asked to do it, seeing the first flight. Please share what was the coolest moment for each of you.
I'll go. I think that for me, probably 2015, the first time that we flew the full-size design in the spaceflight simulator over at JPL, that was probably one of the coolest. Because essentially up to that point, the helicopter had only been tested on, you know, fixed testings, right? So it just looks like a propeller spinning is mounted on top of this big structure. You know, we went through probably 150 tests that looked kind of like that, and then put the helicopter on the floor, and essentially, you know, you hit go, and it took off and it just flew. That was pretty impressive, and that was a big test because that's what we have to do on Mars, right? We can't ever really simulate flight on Mars. You can't simulate the gravity here on Earth. You can attempt with gravity offloads and stuff, but you know, so demonstrating that that actually was feasible, that was a pretty big moment for me.
How about for you, Sean?
For me, there was actually two moments. The first one was when we were at JPL and they said, yeah, we're looking at a Mars helicopter. And it's like, wow, how amazing is that? You know, because I think we all have an intrinsic feel for how difficult that is. You know, 1% of the Earth's atmosphere, you know, atmospheric pressure, the dust, the harsh conditions, the power and weight constraints, and it's like, wow, that's just really amazing. And then the second one was seeing it fly, just amazing. And then having your kids say, "Hey, Dad, does your company have material on that?" And it's like, "Oh yeah," and that's really neat. So.
And Eric?
You know, I think the highlight of this program for me was probably when AeroVironment and JPL were willing and accommodating to allow Toray to share in the kind of the press side of this. We support so many military and defense programs that we obviously can't talk about, and here's a science mission that is inspiring future generations that we can go pump out through our networks and through people like you, Dan, and HAI, and just, you know, we do business with people and we like to talk about it, and we thank our customers and NASA for everything they do for us.
Here.
Okay, gentlemen, I can't tell you how much I appreciate your time this afternoon. I can honestly say without reservation that this is probably the most technical briefing presentation we've had. I'm not ashamed to admit that there were words that I saw on screen that you used that I'd never heard before. So I really enjoyed it. I hope our audience really enjoyed it. We will certainly look forward to seeing how the future of the Mars helicopter goes, and look for more work from Toray and AeroVironment in the future. Gentlemen, thank you so much for your time today.
Our pleasure. Thank you to all of you.
Thank you, Dan.
We do have a few things we need to wrap up with real quick. I will get my screen shared here real fast. There we go. Save the date for next week's webinar. That'll be May 6th, the HAI at Work, HAI Virtual Safety Symposium. This is an event we normally hold at Heli Expo every year. It is always well attended. It's usually on Monday of the show. This will be an NTSB fatal accident review. And we have investigators, accident investigators from the NTSB, from the FAA, and from the industry who will come in and talk about an accident, break it down, and hopefully everybody can learn something from it and help to prevent future accidents. Go. Do appreciate your feedback. We have a follow-up questionnaire that's coming shortly. Please tell us everything that you like about a topic, what you didn't like. This goes in for all topics, not just today's, but past topics. And we also look for suggested future topics. So let us know what you'd like to see us talk about. Also, please let us know how HAI is doing for the industry and for you. Contact president at rotor.org with your challenges. We are doing our best to serve our members, and so we're here to serve you. For those of you who stuck around, we do have kind of something fun. This is not a giveaway, but in honor of the Mars flight, we did rename Helicopter Association International to Helicopter Association Interplanetary. If you're interested in these, any of this gear, we do have it available on our website. If you go to the About section, go to the HAI store, or you can go directly to this web address, everythinghelicopters.com. And I'll leave this up for a second if you want to do a screen capture or catch it with your phone. But we've got t-shirts, we've got mugs, we have water bottles, we've got a couple of different products, we've got a couple of different designs. So don't feel like what I just showed you is the only thing that's available. This is a literally once in a lifetime event. This is a milestone that people will talk about for the future, throughout the future of aviation. The Mars helicopter is an astonishing feat. And so we are very proud of NASA and JPL and congratulate them once again on, well, of course, in Toray and AeroVironment and all the other companies that were involved on such an amazing feat of engineering and just the thinking that goes into that as well. So that is it for today. We do appreciate your time. Thank you for attending. Until next week, we ask that you be safe, that you fly safe, and we will see you again very soon.